9 1-800.
We live in an age where the chance of
sounds incredibly complex. It sounds like students, you need to have abilities that span. I'm really geeking out here.
It so happens there are 2 vials of 500 eggs each. Diapause refers to the hibernation.
Stay cool, Crip.
I knew I could do it.
I knew I could only get you once, though.
If I could get procedures to quit laughing over here. Hibernation cycle of the larva.
I think our audience is familiar with GPS, right? We use satellites to determine our position here on Earth. They send us signals. We have a GPS receiver on our phone or in our car. And it sounds like in your case, you're doing something a little different, but it's still with positioning. And you're saying the positioning of the satellites themselves in space relative to each other is super important. Can you say why that's important?
The reason why the positioning is important is if you're going to have, let's say, for example, a formation of satellites, and they're going to coordinate measurements. For us, we have several applications that we want to know. We want to know, without getting into too much detail, information about Earth's time variable gravity, or we want to know its shape. So we're going to send maybe laser measurements from the satellite to the surface. And those measurements are only as accurate as you know where your satellites are.
I see.
And so we are using GPS to track our satellites, but we're using additional information to try to get it as precise as possible.
I see. Yeah, makes tons of sense. We see these very high precision photographs from space, but you have other things that you want to get high precision, and that only is as good as the precision.
Roger, Hank, you remember about 2 weeks ago when we were talking about the clunkety-clunk noise down in the command module?
Yes. It's not back, is it?
Yeah, it's back. It wasn't as severe. You couldn't feel it as much as you could just hear it.
You're saying is actually satellites can be small things, and people out there might be saying, "Hey, can I come up with something and put it on a rocket?" And it sounds like kind of, but not really. I mean,
you can. And there is a tremendous amount of work that needs to get done because the satellites, even though they're small, they're still a fully functional spacecraft, and they have all of the systems that a major spacecraft would have. So they have a power system, they have communications, they have computing, they have a structure, and it all needs to survive the environment of space. And you also need to go through some regulatory hurdles as well. You can't just throw up something that is going to beacon things or take images of things. You need approvals for a lot of that. And so, yes, they are small, but they have to go through almost the same process as a major mission. But I do want to mention that this SmallSat Express is interesting in that it is a satellite that's being managed by this company, Spaceflight, but 70 other small satellites are going up at the same time.
Oh, wow.
So it's one of the larger single launches of satellites to go up on an individual rocket.
And are those mostly other universities that are doing the small satellites, or is it all kinds of...
If you go and you look at the list, I think the division, they're from all over the world, so a lot of universities, a lot of small companies. There are other larger companies, so it's a full mixture from satellites from all across the world, but I think maybe 2/3 of them are university and small companies, startup companies that are looking to demonstrate a technology.
When you were describing the 2 satellites that are going to be launched, it sounds incredibly complex. It sounds like you need to have skills, you need to have students, you need to have abilities that span a huge array of things. Can you talk about that? Can you talk about a little bit about your research group?
The experience of actually designing, building, and assembling the satellite has been, for me, extremely educational. It's been very enriching, both for myself and for the students. And it is easy when you just talk about it and you see them. You'll see the satellites, and on the outside it looks relatively simple. It's a box. But it's very easy to underestimate the effort that goes into all of that because It is an extremely complex and challenging thing to build, especially because it's so small. And the integration phase in particular, and that's where, the students at Georgia Tech, they're very well trained for the design aspects of it. They'll take a computer-aided design course, and they know about the dynamics or maybe the orbital mechanics, so they know the theory and the mathematics about it all. But they've often never had the chance to actually implement this in real life on a satellite mission that needs to work. There's no room for failure on a satellite, because once it goes up in orbit, if it fails, you can't bring it down and fix it, and there's no servicing mission that's going to save your small satellite. So it has to work 100%. And so the students working on these small satellite projects, they really get to enrich their experience here, because they get to apply this knowledge that they learn in the classrooms to real world problems, and it's hardware. So they're working on, it's an actual satellite, and it's a hands-on environment. So they need to develop a lot of other skills that they don't necessarily have. Yeah. They need to learn to work together. They need management skills. We have deadlines to meet. We have reporting to do. We have licenses to apply for. So they need to develop their writing skills, public speaking, in addition to just the pure technical skills of finally building something. And when you finally go to build something, for everyone who's done that before, who've actually had an idea, designed it, and then actually went to build it, you find out all of the things that you didn't find, didn't design in advance. And everything just comes out of the woodwork for these things. We've had components fail at the last. We've had to make last-minute design changes, and so many little things. Many all-nighters were had building these satellites. But at the end, you really get an understanding of what it takes to build the satellites and get them ready. And that's only part of the story, right? Only building is just part of it. We still have to launch it, do mission operations, process the data. These missions have a goal and a purpose. So that's really the end goal of all of this. So this is only part of this whole experience.
Hey, did you find them?
Yeah, that rascal left us some goodies.
How about that?
All gaily wrapped, Christmas paper and ribbon and the whole bit.
Yeah, I was a little puzzled the other night when you called down and said you had one present to put under the tree.
I should mention also that this particular mission will be tracked by ground-based laser ranging systems. So there are systems, there's a whole network of, think of telescopes with lasers on them that track precisely where the satellites are. We have these mirrors or these retroreflectors on the bottom side. So we're able to really precisely track the location of these satellites to verify the positions that we hope to get. And there's all sorts of secondary experiments, because you could almost treat these satellites as a piece of space debris. It's a space debris that we just happen to know precisely where it is.
I see.
But let's model that, or let's say, what if we only got a few images of it, and we wanted to predict in time, and maybe we needed better atmospheric models or better orbit trajectory analysis. We could test these theories out and use our satellites, because we know where they are, to validate those models. So there's a lot of secondary science and other aspects to this mission.
As you were describing a little bit earlier, some of the aspects of your satellites, the one that caught my eye, I'm an electrical engineer. I think you said there's no power source on these, or what?
No propulsion system.
No propulsion system.
So there are plenty of electronics. In fact, that's one of the things that we've learned a lot doing our custom electronics. Because we try to buy as many just off-the-shelf components as we can, but we've also learned that there's just some instances where you just have to make your...
Not having a propulsion system asks, to me, my mind says, okay, well then, how do you're going to want to move the satellite either relative to each other or in place. And then I think you talked about atmosphere.
That's
I'm
right.
really geeking out here. So you're able to, even though you don't need propulsion, you can, because of the atmosphere, the thin atmosphere around the satellites, be able to adjust.
You think of two satellites, even the simplified case, where it's one edge is a big flat plate, and if you turn it 90 degrees, it would be very, let's say, much less surface area. And now think about both of them being in the same orientation, and you just turn one. Now the drag force on one is different than the drag force on the other, and that's where this term differential drag comes in. So then they're going to change position. And it's a little counterintuitive how you actually change the inner satellite position of each other, but that's the basic concept of it, that you're changing the drag force on each satellite, but one at a time, so that then you can control their inner satellite.
Good morning at 8:35 Central Standard Time. The crew will reach the halfway point in the scheduled 84-day mission.
flying through my brain. I mean, if really your experiment is to try to measure down to centimeter, millimeter scale, the ability. I keep going through this. He's not an aerospace engineer. He's like about 10 different kinds of engineers.
Exactly. And a earth scientist as well, and a planetary scientist. All mixed together.
Because, I mean, it at the high level, it makes sense that an aerospace engineer is designing a satellite, but like when we get down to it, and all the pieces that need to work together, tens of thousands of miles. And you started to talk a little bit about some of these other projects. Can you share some information about the other projects that are going on?
And one of the other missions that I have in the works is a NASA-sponsored mission. So it was nice that we're talking about NASA because it is sort of a mini NASA. This was a mission called the Tethering and Ranging Mission of the Georgia Institute of Technology, or TARGET for short when you do the acronym. So TARGET is a mission that is also very exciting. It's a little bit larger than the range mission, and it's just, I'll say, its goal is to test what we call an imaging LiDAR. So a LiDAR system is, again, this ranging system. So think of a system that could generate a three-dimensional map of a surface, and that's what this LiDAR system can do. And what we want to do is create a compact imaging LiDAR for planetary application.
I see. Mm-hmm.
So the goal is if we build this system, we can now, next time, let's say NASA goes to Mars or to Saturn or Jupiter, that we have a small satellite, a CubeSat, as a ride share in a similar concept that we have around Earth, that we spin off, and we get to go explore maybe other aspects, other celestial bodies that we don't know about, moons or comets or asteroids. And we can do this in this very small, compact satellite. And so this TARGET mission, it is NASA sponsored. So again, it's a whole team of students. We have 25 students currently working on it, developing all sorts of things. And it's a really interesting mission concept because we're going to test, again, a lot of new technologies. So the LiDAR system itself is a new instrument. We're hoping to do this for very low cost and make it very robust and high precision. But the way that we're going to test this LiDAR system is we're going to tether out. So think of like a fishing wire on a very thin tether. We're going to tether out what we call an inflatable. If you looked at it, you might look at it as a balloon. So we're going to tether out something about 10 meters, so 30 feet. We're going to inflate it, and that is going to be our, let's say, sample moon. So we're going to validate our imaging LiDAR on this inflated target, hence the name TARGET. And the challenging part is going to be, the nice thing is we'll know everything about it because we built the target, so we'll be able to verify that the images, the 3D maps that we're getting from imaging this small target are correct. And then the challenging part at the end is the very last part of the mission. And the reason we have the tether is because as soon as you cut that tether, the target is only within the vicinity of the main spacecraft for a few hours. But that's exactly what we're going to do at the very end of the mission. We're going to cut the tether, and this thing is going to free float away. And we are going to use all of our satellite systems to continue to track this and continue to range to it and gather data on it as it goes 10, 20 kilometers away. And this is representative of a scenario where you had a CubeSat and you're flying it by deep space navigation can get you within 10, 20 kilometers of an object pretty reliably. And so this is why we want to target this. If we can demonstrate that we can track this object as it goes 10 kilometers away, that's pretty representative of us being able to fly by a comet or an asteroid or maybe a particular surface feature on a moon. And there are a lot of applications for this. So you could think of going to a moon and doing some reconnaissance. There are a lot of destinations that NASA is considering for future manned flight. Europa or Phobos, these are moons of planets. And it would be great to send this small imaging system there to map out to make sure that the area is safe, make sure there's not any large features, make sure there's not going to be something terrible that happens if you send a manned lander down. But it's also, if you think about what the systems that are involved, lasers, very similar to what we're doing with the intersatellite ranging systems on range, except we also want to demonstrate laser communications. So then you could think about using the same LiDAR system as a way to either gather mapping data or reconnaissance data. You can actually use it as you approach the satellite or the moon as ranging information, so you could use it for your guidance. And then you could conceivably, after you gather all this information, turn the whole spacecraft back towards Earth and use high-speed laser communications to transmit all that data back to Earth at a very high data rate. And so this ties into another theme, another project that we have that we recently got over the summer that involves just that very thing, developing yet another spaceborne high data rate, and this is gigabit per second type data streams from space to ground. And so this is working, this other project that I'm just talking about that was just started over the summer. We hope to demonstrate that on the space station. So the objective is to develop this laser communication terminal that was originally developed at JPL, but we're going to take it, we're going to miniaturize it, and we're going to demonstrate, gigabit up to 10 gigabits per second from space to ground. And that's a pretty enabling technology. If you can think about even sending 10 gigabits of data or a network of, think, tens or hundreds of these satellites that can all communicate at 10 gigabits per second, or a planetary mission that could live stream high HD video from wherever they are, it's really enabling. So these are the types of things that we're working on.
As a taxpayer, the kind of just the idea of letting robots, and as you know, I think people know, robots are becoming more and more human-like, but the idea of multiple missions of robots to go and explore someplace before we put humans does make a bunch of sense, because for all the risk factors you talk about, but maybe even just purely from a cost standpoint, that makes sense. But I mean, I know we're learning so much. We have learned so much through the space programs that, whether we're sending robots or humans, we're going to continue to learn, a huge amount. What a fantastic opportunity, for students to study undergrad or grad because of that whole system. And at the end of the day, it's really teamwork. And I think that's the thing you emphasize over and over again. Our students develop, good solid skills, engineering skills, but even more than ever, that doesn't mean a lot unless you really know how to work with a team. And it seems like these projects, dare I use the word, are just perfect scenarios for students and others to just, use their skills, but more importantly, learn about teams. And so talk about how you help the students build the teams.
A lot of it is just learn by doing. When we take in students, we try to take them as freshmen, as sophomore, because we know that development process takes many years before they're ready to take on more complicated tasks. And it also gives them this exposure to decide whether they enjoy this type of work or not. Many of them don't, and that's fine. Many of them really embrace it, and they absorb things, and they may not come in with necessarily good programming skills, but they realize that's important, and then they develop those skills over the next couple of years, and now they're working on some particular component or an embedded system. Or somebody who comes in, for example, with some of the laser projects, they're not necessarily, you don't get that training to become an optics expert or to work with laser communication systems. That's not part of the undergraduate curriculum, so you have to learn on the job. So much of what we look for, and the students that are really successful, are just those students who are just really ready to be open-minded, to give it their all, to learn new skills, and as part of that, they learn how to coordinate with other teams, because you have to coordinate with the power subsystem. You have to talk with there's the main onboard computing system, and if you have your payload, which is, say, the laser system, all of that has to be integrated together. They can't work on things on an island, and so we have these regular weekly meetings. We have formal reviews with NASA that we have to pass, and these are all big occasions to finally get everything together to coordinate with each other, and so it is important. And I think it's also very representative of what you will find when you actually go into the workplace. That you have to work along other people. You have to solve problems. It's not about necessarily your individual subsystem, but it's about the whole mission being successful, and that's the overriding goal. And I think most of the students embrace that.
Being up here and being able to see the stars as you can, and look back at the Earth and see your own sun as a star, makes you much more conscious of that.